Welcome you all. In the last session, I explained you about the concept of filtering in frequency domain. So, if you want to understand the details of image processing, we need to understand the image enhancement in frequency domain also. In the spatial domain, we directly manipulate the pixel value, but in frequency domain, we modify the Fourier transform. So, we can use either 1D or 2D. So, 1D discrete Fourier transformation or 2D discrete Fourier transformation. So, in the last session I explained both one-dimensional discrete Fourier transformation and two-dimensional discrete Fourier transformation. So, when we perform a filtering operation, we need to follow certain steps. So, in frequency domain filtering, first the input image is required to pre-process. So, in the pre-processing step, we multiply the input image f of x comma y by minus 1 to the power of x plus 1. Okay, that is pre-processing. Next step is discrete Fourier transformation. So, after performing discrete Fourier transformation, we get the output f of u comma v. So, in the filtering operation, we multiply f of u comma v into h of u comma v. So, f of u comma v is the Fourier transform output of f of x comma y, and h of u comma v is a filtered function. So, after multiplying f of u comma v with h of u comma v, we get the output g of u comma v. So, g of u comma v is the filtered output. So, after performing filtering operation, we need to get back the output image in the form of spatial domain. So, to get the output in spatial domain, we need to do inverse Fourier transformation. So, after performing inverse Fourier transformation, we get the output in the spatial domain. So, after performing inverse Fourier transformation, we get the real part of the output. So, in the frequency domain, the output contains both real part and imaginary part. So, in the filtering process, we select only the real part of the output. So, after that, we finally multiply minus 1 to the power of x plus 1 in order to cancel the multiplication at the pre-processing step. So, in the pre-processing step, we multiply the f of x comma y by minus 1 to the power of x plus 1. So, in order to cancel the multiplication, at the end, we multiply g of x comma y into minus 1 to the power of x comma minus 1 to the power of x plus 1. So, we get final output g of x comma y. So, g of x comma y is the filtered output in spatial domain. So, after that we discuss in the last session. So, in this session I am going to explain the smoothing filter in frequency domain. So, smoothing filter in frequency domain. So, in the last class itself I explained there are two types of filters in frequency domain. One is low pass filter and other one is high pass filter. So, low pass filter is also called a smoothing filter and high pass filter is also called sharpening filter. So, the main purpose of smoothing filter is to attenuate high frequency values. So, in the image, high frequency values are related to the sharp edges and noise. So, in order to eliminate the noise, in order to eliminate the sharp edges and changes, we need to do the filtering operation. So, that is we need to perform a smoothing operation. So, the general model of smoothing is, or general model of filtering in frequency domain is represented by g of u comma v is equal to f of u comma v into h of u comma v. So, g of u comma v is the filtered output, in frequency domain. Then f of u comma v is the discrete Fourier transformation. So, DFT of f of x comma y. So, this is a Fourier transformation output, that is f of u comma v, then h of u comma v is the filter function. H of u comma v is the filter function. So, this is a general model of filtering in frequency domain. So, here the filter function is, we can use different filter function depends upon the type of image. So, if in case if you want to eliminate the noise, or if you want to attenuate high frequency value, then we need to use a different mask, a different filter. Okay, depends upon the image, depends upon the purpose, we select different filter coefficient. Okay, this is a general mode of filter in frequency domain. Okay, when you are performing smoothing operation, in the smoothing process, it attenuates all high frequency values and it allows only the frequency values less than the specified cutoff frequency. So, specified cutoff frequency. So, smoothing is also called as low pass filter. The purpose of the low pass filter is to attenuate all high frequency components, high frequency values, and it allows only low pass frequency. So, it attenuates all high frequency values. So, the output of a smoothing filter is the blurred version. So, sometimes the output is blurred. Okay. In smoothing operation, we use three different filters, that is ideal low pass filter, ideal low pass filter, Butterworth low pass filter, and Gaussian low pass filter. So, first one is ideal low pass filter, ILPF, then BLPF, then GLPF. So, ILPF means ideal low pass filter, BLPF Butterworth low pass filter, and GLPF Gaussian low pass filter. So, these are three different filters we use in smoothing operation. So, first one is ideal low pass filter, Butterworth low pass filter, and the last one is Gaussian low pass filter. Okay, let us move on to ideal low pass filter. Ideal low pass filter. The ideal low pass filter is the simplest filter. So, here it attenuates all the low frequency, attenuates all high frequency values, and by allowing only low frequency values. So, the ideal low pass filter is represented by h of u comma v is equal to 1 if d of u comma v less than or equal to d naught, less than or equal to d naught. 0 if d of u comma v greater than 0. Okay. In the ideal low pass filter, the function h of u comma v is equal to 1 if d of u comma v less than or equal to d0, and 0 if d of u comma v greater than d0. So, if the distance value is less than d0, then the value is 1. If in case if d of u comma v greater than d0, then it becomes 0. So, here d is the distance function, d is distance. Okay, it is a non-negative value. Then here also cutoff frequency, cutoff frequency. So, cutoff frequency is non-negative value. Cutoff frequency is non-negative value. So, if the value is, if the value is non-negative value, then this value will be compared with the distance value. So, when finding the distance, we use Euclidean distance. We use Euclidean distance. So, d of u comma v is equal to u minus m divided by 2 whole square plus v minus n divided by 2 whole square. So, this is the equivalent distance formula. D of u comma v is equal to u minus m divided by 2 whole square plus v minus n divided by 2 whole square. So, m and n represent the row. So, here you consider the square. We consider the square. So, first the center, we consider center. This center is calculated by m by 2 and n by 2, m by 2 and n by 2. So, this direction is u and this direction is v. So, first we calculate the distance value. So, if the distance value is less than d0, then it allows only the frequency which is less than d0. If the frequency value is greater than d0, then it will alternate all the frequency. Okay, this is the ideal low pass filter equation. Now, I will show the pictorial representation of ideal low pass filter. Okay, in the ideal low pass filter, now we consider this a rectangle frequency. Rectangle frequency. This is u and this will be v. Okay, this is h of u comma v. H of u comma v. So, it allows only the frequency which is less than d0, So, it will consider from the center fixer value. So, with if the distance value is less than cutoff frequency, it allows, and remaining fixer value is attenuated. Remaining frequency is attenuated. Okay, now you consider this. Okay, in this case, this center value is 1 and remaining value is 0. So, this pixel value is 0 and this value is 1. So, this is u and v, u and v, u and v. Okay. Now, here it start comparing from the center rectangle. So, rectangle center. So, here it compares up to d0 value. If it is less than d0, then this value is 1 and remaining value is 0. So, in this case, in the image term, the 1 is represented as white and 0 is represent 1 is white and 0 is black. So, 0 is black. So, in Gaussian filter, in the ideal low pass filter, it allows only the frequency which is less than d0 and it attenuates all the high frequency values. So, here it is a fixed cutoff. There are only two possible values. One value is 0 and another value is 1. So, you can see the graph. This is 1 h of u comma v. So, this is d of u comma v. So, this will be the cutoff frequency, that is d0. If the intensity value, if the intensity or frequency value less than d0 becomes 1, less than d0 is become 1 and remaining frequency is 0. So, if it is within the cutoff frequency, then it is 1 and above the cutoff frequency will be 0. So, in the ideal low pass filter output, if distance value is less, if in case if you consider a distance value or cutoff frequency value phi, then the image will be blurred. So, the output image will be blurred, and it also produce a ringing effect. So, it also produce a ringing effect. So, if in case if you increase the distance value, if in case if you increase the cutoff frequency value, then the output will be a more clear output, and there is no ringing effect in the output. There is no ringing effect in the output. So, if the distance value is less, D0 value is less, so output image gets blurred and it contains ringing effect. If D0 value is high, then there is no ringing effect and there is no blurring effect. Okay. Now, I will show you the implementation of ideal low pass filter. Okay. Just now I explained the ideal low pass filter. So, the ideal low pass filter is represented by h of u comma v is equal to 1 if d of u comma v less than d0, 0 if d of u comma v greater than d0. So, d0 is cutoff frequency, where d is the distance value. So, d of u comma v is equal to u minus m divided by 2 whole square plus v minus n divided by 2 whole square and 1 by 2. So, this can also be written as square root of u minus m divided by 2 whole square plus v minus n divided by 2 whole square. So, here in ideal low pass filter, it allows only the frequency which is less than d0 value. So, less than d0 value is allowed and remaining value is attenuated. You can see in this figure, it allows only the frequency within the range of cutoff frequency. So, here in the second image you can see the center value is white and remaining value is 0. So, center value is 1 and surrounding value is 0. So, in the graph, if d value is less than d0, that frequency becomes 1, greater than d0 it becomes 0 value. So, the property ideal and can be implemented in computer. No physical is equal to non-actual and non-real. Okay. Here I already mentioned there is a ringing effect and blurring effect in ideal low pass filter. So, first image is the input image, then this is the output image. If D0 is 5, you can see in this image the content is not clearly visible. So, we won't fetch any information from the output image because it contains more blurriness. If in case if D0 is increased to 15, there is a blurring effect and also ringing effect. So, you can see in the second image, third image, that is D0 value is 30. Here the image is contain little bit blurring effect and ringing effect is more. So, ringing means the image contains the surroundings. So, image contains the surrounding. Example, if you consider A, there is like a ringing effect on the A. The surrounding A contains some blurriness and ringing effect. If in case if you increase D0 value is 80, you can see here there is no ringing effect and there is no blurring effect. So, there is no ringing effect and there is no blurring effect if if cutoff frequency D0 is increased. Okay. This is an example for ideal low pass filter. This is a MATLAB code for ideal low pass filter. So, here first I am reading the image. The image is moon. The format is TIP format. First I will get the size of the image. So, m rows and n columns. So, m represent height and n represent width of the image. Okay. After that, in the frequency domain, first we need to find the Fourier transformation of the input image. So, here we perform Fourier transformation. So, in MATLAB, this is a function is used for performing Fourier transformation. So FFT2 of double input image. So here input is a spatial domain image. So input is given. Then it performs a Fourier transformation. After performing Fourier transformation, the value ranges from 0 to 1. Next, here I have set the cutoff frequency D0 is 30. So initially I have set D0 is 30. Then here we calculate the distance value. So distance value is u minus m by 2, v minus n by 2. So here we calculate the d value. So here d value, the u value is u value and v value. So u is equal to u minus m. So u minus m. So here u set as 0 to m minus 1. So find the middle value greater than m by 2. Next, we find the distance value, that is d is equal to square root of u square plus v square. U square plus v square. So we u dot power 2. So we already know u minus m divided by 2 whole square and v divided by 2 n by whole square. So u minus n divided by 2 whole square. So here we calculate the distance value. So after finding the distance value, if we calculate f, so double d less than d0. So if the value is less than d0, then the convolution mask or filter mask h becomes 1, otherwise h value is 0. After that we multiplied h with f. So we know the basic model of filtering. The filtering model is g of u comma v is equal to h of u comma v into f of u comma v. So here g is equal to h into f. So h is a filter function and ft image is the Fourier transform output. So this performs filtering operation. After that we need to get the real part of the image, real part of the output. So output, then we need to perform the inverse operation. So here output is equal to real of IFFTF. So FFT2 is a discrete Fourier transformation and IFFT2 is inverse discrete Fourier transformation. So we get the inverse transformation of the output G by extracting only the real part. So after that we are displaying the output. So first is the input image and second is the output image. So you can see the output. So first image is the input image and the second image is the output image. So here output is little bit blur and there is a ringing effect. If in case if you change the value of D0 by 200, then you can see the output. You can see here output, in this output there is no ringing effect and there is no blurring effect. So here the D0 value is 200, then no ringing effect, and there is no blurring effect. If in case if you change this value as 3, now we can see in this output the image is not clear, the image is completely blurred, so we won't get any information from the output. So if D0 value is high, no ringing effect, then there is no blurring effect. If D0 value is less, there is a ringing effect and there is a blurring effect. So this is about ideal low pass filter implementation. Okay, the next filter is the Butterworth low pass filter. Butterworth low pass filter. So here the Butterworth low pass filter, the filtering operations perform based on the order, based on the nth order. So the function of Butterworth low pass filter is h of u comma v is equal to 1 divided by 1 plus d of u comma v divided by d naught to the power of 2n, to the power of 2n. So, n is the order. So, n represent the order. Then here d of u comma v represent distance function. Then this d0 is cutoff frequency. Cutoff frequency. So, here cutoff frequency d0 is a non-negative value, So, in the Butterworth low pass filter, the Butterworth low pass filter, this is h of u comma v. This is u and v. So, in Butterworth low pass filter, the output is depends upon the order. Okay, if in case if this n is equal to 1, next n is equal to 2, n is equal to 5. This is d of u comma v, this is 1, and h of u comma v. So, here if in case if the order of the Butterworth low pass filter is 1, if the order of Butterworth low pass filter, that is if n is equal to 1, so in this there is no ringing effect. So, in the order 2, there is a ringing effect, but it is not perceivable. So, if in case if you increase the higher order, then there will be a ringing effect. So, if in case if the cutoff frequency is less, then the image get little bit blur. So, compared to ideal low pass filter, in the ideal low pass filter there is more ringing effect and blurring effect, but in Butterworth low pass filter less ringing effect and less blurring effect. So, the output depends upon the order. So, one more difference between the ideal low pass filter and Butterworth low pass filter is, in the ideal low pass filter there is a clear cutoff frequency, that is 0 and 1, but in Butterworth low pass filter, the value is start slowly varying from 1 to 0. Slowly varying from 0 to 1. So 1 to 0. So, in center fixer value is white and slowly it changes and it becomes black. So, slowly change from 1 to 0. Slowly change from 1 to 0. So, here there is no clear cutoff. In the Butterworth low pass filter. So, compared to ideal low pass filter, there is less ringing effect and there is less blurring effect in Butterworth low pass filter. So, I will show you the implementation of Butterworth low pass filter and with some example output of Butterworth low pass filter output. So, I already mentioned, if the distance value or if the cutoff frequency is less, there will be a blurring effect. If cutoff frequency is high, if in case if your cutoff frequency is 200 or 250 something, then the output will be the clear output. So, the output is clear, then there is no ringing effect and there is no blurring effect in the output. Okay, just now I explained Butterworth low pass filter method. So, in the Butterworth low pass filter, the function h of u comma v is equal to 1 divided by 1 plus d of u comma v divided by d naught to the power of 2n. So, here the transformation function Butterworth low pass filter of order n. So, it depends upon the order n and the cutoff frequency. So, d of u comma v, if h of u comma v is equal to 0.5 when d of u comma v is equal to d naught. So I already mentioned the output depends upon the order value. So order value n0, n is equal to 1, n is equal to 2, n is equal to 3. So in the ideal low pass filter, there is a clear cutoff between the values, that is 0 or 1, but in this Butterworth low pass filter, the value is vary from 0 to 1, vary from 0 to 1. So you can see in this image, the center value starts with white 1 and it slowly changes to black, So in Butterworth low pass filter, if order n is equal to low value, means 1 or 2, there is no ringing effect, but if order is increased, there is a ringing effect. So unlike ideal low pass filter, Butterworth low pass filter transfer function does not have sharp discontinuity and has clear cutoff between passed and the filter frequency. A Butterworth low pass Butterworth filter order 1 has no ringing effect, generally imperceptible in the filter order 2, but can become a significant factor in the filters of higher order. So you can see in this example, if D0 is 5, there is a blurring effect, the image is not clear. Then if D0 is 15, there is a small ringing effect and there is a blurring effect. If you change the order cutoff frequency 80, then there is no ringing effect. There is no ringing effect and there is no blurring effect. There is no ringing effect and there is no blurring effect. So you can say the output of the Butterworth low pass filter with a distance D0 is 230. The output image looks very similar to the input image. Okay, this is about the Butterworth low pass filter. So you can see here in the Butterworth low pass filter, n is equal to 1, there is no ringing effect. When n is equal to 2, a little bit ringing effect, but in case of n is equal to 5 and n is equal to 20, you can see here there is more ringing effect. So you can clearly perceive there is a circle on the image. There is a circle on the image. Okay, this blurred circle is called ringing effect. Just now I explained the concept of Butterworth low pass filter. So in the Butterworth low pass filter, we specify the order. Okay, now here in this program, this is implementation, MATLAB implementation. So here I am reading a image moon of TIFF format. So first I'll get the size of the image, that is width and height and width. So height represented by m and width represented by n. Then before performing the filtering operation, first we need to transfer the image into frequency domain. So first we perform Fourier transformation. So Fourier transformation is represented by FFT2. So FFT2 is a MATLAB code, a MATLAB function for transferring the image into frequency domain. So first we transform the image. Then here I am setting n value is equal to 1 and d value is equal to 150. Later I will get the size u and v. So index, find u greater than m by 2, means index is the center pixel value. Index is center pixel, center location, index x and index y. So this index x means height and width. So here IDW width. So first we get index. After that we are finding u index is equal to u minus em, u minus m. So when we are finding the distance value, so the formula is square root of u minus m divided by whole square plus v minus n divided by 2 whole square. So first we need to find u minus m. So u minus m is u index and v minus n is v index. After that we calculate the value distance, that is d is equal to square root of u dot power, then v dot power means u dot power means u minus m by 2 whole square and v minus n divided by 2 whole square. So first we find the d value. After that we calculate the filter function, that is h. So we know the formula for h. So h is equal to h of u comma v is equal to 1 divided by 1 plus d of u comma v divided by d naught into d naught to the power of 2n. So here we calculate the h function. After finding h, we multiplied h with f. So we know the basic model of filtering, that is basic model is g of u comma v is equal to h of u comma v into f of u comma v. So here g of u comma v means g is equal to h into ft of image. So ft image is f of u comma v. After that we need to get the output in the frequency spatial domain. So in order to get the output in spatial domain, we need to do inverse Fourier transformation of the real part. So output image is equal to real of IFFT2 double G. So here we get inverse transformation. After that I am displaying the output. Okay, now you can see the output. Here in this case the order is 1, nth order is 1 and distance value is 150. Now here I will change the d naught value is 5 and the distance value number of order is 8. So the output is, you can see here the output is blurred output. So output is not clear because the D0 value is 5 and order is 8. So if in case if we change the order, if we change the distance value to 80, now you can see, so if the distance value is 80, then the output is clear output. So here there is no blurring effect in the output. There is no blurring effect in the output. Okay, this is okay. The next filter is the Gaussian low pass filter. In Gaussian low pass filter, the filter function h of u comma v is equal to e to the power of minus d square u comma v divided by 2 sigma square. So here if in case if you consider sigma d square, sorry, d naught is equal to sigma square, sigma d naught is equal to sigma, then h of u comma v is represented as e to the power of minus d square u comma v divided by 2 d naught square. 2 d naught square. Okay, here also d is distance function, d is distance and d0 is cutoff frequency. D0 is cutoff frequency. So in Gaussian low pass filter, once again we consider the rectangle frequency. This is u and v. This is h of u comma v, h of u comma v. Then here also in the Butterworth low pass filter we consider the order, but here we consider the d naught value. So if in case d naught is equal to 0 or d naught is equal to 1, then here a little bit, then d naught is equal to 1, this is d naught is equal to 3, then d naught is equal to 5. So this represents h of u comma v, this is 1, then d of u comma v. So here the output is depends upon the d naught value. So if d naught is if d naught is less, means if a d naught value is 2 or 5, then there is a blurring effect. If the d value is higher value, then if the d value is 30, 40 or 100, then there is no blurring effect, there is no ringing effect. So the main difference between the ideal low pass filter and Gaussian filter, in the Gaussian filter there is no ringing effect and there is no blurring effect, but in the ideal low pass filter there is a blurring effect. There is a blurring effect in the ideal low pass filter, but there is no blurring effect in Gaussian high pass filter. So Gaussian low pass filter. So here also in the ideal low pass filter there is a clear cutoff frequency value, but in Gaussian low pass filter, so center value start with 1, then slowly change to 0, then it is slowly change to 0. But in the Butterworth, in the ideal low pass filter there is a clear cutoff, because the center value is 1 and the surrounding value is 0. But in case of ideal Butterworth low pass filter and Gaussian low pass filter, the center value start with 1 and slowly change to 0. Slowly change to 0. This is U and V. U and V. So the main difference between the Butterworth low pass filter and Gaussian low pass filter is, in the Butterworth low pass filter there is a little bit ringing effect, but in Gaussian low pass filter there is no ringing effect. There is no ringing effect. Okay, that's about the Gaussian low pass filter function. So now I will demonstrate the implementation of Gaussian low pass filter with some example. So the Gaussian filter function is represented by h of u comma v is equal to e to the power of minus d square u comma v divided by 2 sigma square if sigma is equal to d naught. Otherwise we can write h of u comma v is equal to e to the power of minus d square u comma v divided by 2 d naught square. So here in the ideal low pass filter there is a clear cutoff between 0 and 1, but in the case of Gaussian low pass filter the value is center pixel start with white and it is slowly changed to black. So there is no clear cutoff in the frequency values. So you can see the example output of Gaussian low pass filter. So in the Gaussian low pass filter, if D0 is 5, there is a blurring effect, and if the D0 value is increased, there is no blurring effect. You can see here, if D0 is 15, still it has a blurring effect, and D0 30, little bit blurring effect. If in case of D0 is 80 and 230, there is no blurring effect and there is no ringing effect. So compared to other two filters, that is ideal low pass filter and Butterworth low pass filter, in Gaussian low pass filter there is no ringing effect in the output. There is no ringing effect in the output. Okay, this is the example of Gaussian low pass filter. Okay, just now explain the concept of Gaussian low pass filter. So in the Gaussian low pass filter, we consider the sigma value. So sigma value is equal to d naught value. So based on the cutoff frequency d0, the output will be produced. So there is no ringing effect in the Gaussian low pass filter. So this is a MATLAB code for implementing Gaussian low pass filter. So first we read the image. Here I consider the moon image as an input image. Later here I am setting the d naught value is 100. Then first we scale down the image into 0 to 255, that is f is equal to mat 2 gray value, that is 0 to 255. Then here this is the code for performing pre-processing in the filter, that is input image is multiplied with minus 1 to the power of I plus j. Okay, here pre-processing is performed. Then filtering is performed by calculating d and u. So here d is u minus m to the power of 2 and v minus n by 2 to the power of 2. So here we calculate the distance value. Then h of u comma v is equal to exponential of minus d divided by a minus d divided by a. So d by a is d naught to the power of d naught to the power of 2. So 2d square. So that is 2d square. So xp is equal to minus d of u comma v divided by 2 d power. So here we calculate the filter function. After finding the filter function, the filtering is performed by multiplying filter function with f. So filter function is h and FFT, discrete Fourier transform output is f. So G is equal to f into h. After that we do the inverse transformation of the G output, that is IFFT2. So in the filtering we need to get only the real part, So here we are extracting the real part of the output, that is GP is equal to real of GP. So we get the real part. So after that we need to cancel the multiplication of the image. So in the initial step we multiply input image by minus 1 to the power of I plus 1. So in order to cancel the multiplication, here we multiply the output image by minus 1 to the power of I plus 1. So here g of I comma j is equal to double of g of I comma j into minus 1 to the power of I plus j. So here we cancel the multiplication. Later we display the output of filtering operation. So you can see the output of the Gaussian low pass filter. So this is the input image and this is the output image. So here output is less blurred because I have considered D0 is 100. If I set D0 is equal to 100 or D0 is equal to 10, then you can see the output, it contains the blurring effect. So you can see here there is a blurring effect. The image is not clear because the cutoff frequency is 10. If I change this cutoff frequency to 150, you can see the output. So this is the input image and this is the output image. So output images looks very similar to the input image because the cutoff frequency is 150. Cutoff frequency is 150. Okay. This is about the implementation of Gaussian low pass filter. The fundamental relationship between the spatial domain and frequency domain is based on the convolution theorem. So in the spatial domain, the input image is multiplied with the kernel or convolution mask. So then output image is produced. So in the spatial domain, it considers the neighboring pixel and the filter mask. But in frequency domain, so first the images need to be transferred to frequency domain. So in order to transfer the image into frequency domain, we do Fourier transformation, that is discrete Fourier transformation. Then the filter function also transferred to frequency domain by performing discrete Fourier transformation of the filter function. Later, the function will be multiplied, the image will be multiplied with filter function. Then it produces the frequency domain output. Later, the frequency domain output is converted into spatial domain output by performing inverse Fourier transform. So here in this slide, the green box represents the spatial domain and blue lines and blocks represent the frequency domain. So you can see here in the spatial domain, convolution mask is multiplied with the image. So convolution mask is represented by h of x comma y and image is represented by f of x comma y. So the output is g of x comma y. So the function is r is equal to w1 into z1, w2 into z2 plus w9 into z9. So here w represent the convolution mask and z represent input image. So in the frequency domain, we can represent as f of x comma y into h of x comma y. So in frequency domain, h of u comma v is equal to f of u comma v into h of u comma v. So f of u comma v is the Fourier transformed output of f of x comma y, and h of u comma v is the Fourier transformed output of h of x comma y. Okay, this is a fundamental relationship between or correspondence between the spatial domain and the frequency domain.